All right. So hello everyone. Yeah. So I'm at Université Laval in Quebec City. I'm doing this on Skype. It should work, but it's the first time I do this. I have the Twitter account set up, so I should be looking if anyone tweets at the same time. It's on another screen, and I have my emails, but those are harder to look as I talk. So if you email me, I'll take a look at the end of my presentation. All right, so I decided I should start this little seminar series to try to get some discussions going in the program. I'm talking about privacy for Bayesian modeling, but let me first do a little disclaimer. I am not an expert on privacy for Bayesian modeling. So I've done a little bit of thinking about it, and I'll share some results, but the whole point was to talk about what's involved with privacy for Bayesian modeling and try to foster a little bit of discussion. So hopefully I can manage to do that. So just the general context is, imagine we're trying to publish some output from a Bayesian model, but we want to protect the privacy of the respondents. And there's two main ideas of what that could be like. So the first one is the one that I started thinking about, which would be to publish private draws from the posterior predictive distribution as synthetic data sets. So one big thing in data privacy is a lot of people are creating synthetic data sets by simply sampling from a statistical model that they estimate from the real data. So for example, some of the synthetic data prepared by the Census Bureau, that's what they do. So you fit a model to the real data, and then you sample a synthetic data set. And so there's also a lot of work doing Bayesian modeling for this, where you'd be sampling from the posterior predictive distribution. And the usual argument is that because it's completely synthetic, it's private and there's no confidentiality issues. But with the advance of things like differential privacy, these sort of guidelines have been, I guess not everyone agrees with this opinion. And so the idea is to try to actually give a rigorous guarantee of output such as posterior predictive distribution. So that's one context. And the other one is just simply to publish some draws or information from the posterior distribution of the parameters of interest. So I do, so there's a lot of work for frequentist analysis, trying to publish MLEs with privacy and things like that. And so here we're thinking, doing the same thing, but for a Bayesian analysis. So this is sort of the main goals, I guess. When I talked about private Bayesian modeling, that's what I'm thinking about. So what I'm going to talk about, there's going to be two parts in this talk. And so the first part is I'll be talking about publishing output from a Bayesian model with differential privacy. Okay, so really incorporating differential privacy in that process. And so there's going to be three parts. I'm going to talk first about what we already knew how to do when I started working on this. What I attempted to do, which you'll see wasn't that successful. This is why I'm saying this is partially a discussion seminar. And then I'll briefly into other results, which I was just informed of very recently as the ad for this presentation was published. And then in the second part, I'll talk about something else, which is very related, which is empirical differential privacy. And so the idea there was it was proposed as an easier way to measure the privacy of a Bayesian model. And so I've been studying this. I was very excited because the first way didn't work so well for me. So when people propose an easier way of measuring privacy, I got really excited and I started looking at it. And so I'll tell you what empirical differential privacy is and some results that I got with a student, which are a little bit, I guess, not very good results, in that we sort of find some problems with the definition. But I'll tell you more about that later. Okay, so that's the plan of the talk. So two first parts. One where it's, I guess, not as complete results, and the second, which is based more on a paper that just got accepted recently. And I should have said that if you have any questions, so people that are in Cambridge, you can raise your hands, and I should be able to hear you. And I can follow the Twitter account too. So, yeah. All right, so the first thing is really trying to include differential privacy in Bayesian modeling. So I have a slide here about differential privacy. I think we've all seen this slide a lot of times if you've been part of the program already. So I'm not really going to go into it that more, but basically just the important parts is for differential privacy, you're looking at neighboring data sets. So data sets that differ only by one observation, and then you want to make sure that whatever function you're going to be applying to these data sets and looking at outputs of, you want that function not to depend too much on the specific data set. So you want the probabilities of the outputs to be very similar if you have similar data sets. So that's differential privacy in a nutshell. So we're trying to do that for Bayesian modeling. And so what we already knew how to do when I started thinking about it, there was one example, which is the Dirichlet multinomial model. So here what we're doing is, suppose we have some data x that comes from a multinomial distribution with, so n is just the number, so I use n, so you could imagine is the sample size, and then pi, which is a probability, well, it's a vector of probabilities. And so x comes up from a multinomial. The usual Bayesian conjugate distribution would be to use a conjugate prior, which is a Dirichlet prior, with some parameter gamma. Okay, and so the idea is, that would be the usual model I would use, and now I want to try to do this in a Bayesian way. Well, there was a paper, which is the On the Map paper that you might have heard about, which is really like the only paper that actually implemented differential privacy in a real setting. And so they give an algorithm there, which allows us to sample from the posterior predictive distribution and satisfies differential privacy. And so what the algorithm does, so here's a few details, there's 2 steps to it. And basically what you do is you first sample a parameter from the posterior distribution. And so here we have a conjugate model, and the posterior distribution is, again, a Dirichlet distribution. So my prior was a Dirichlet gamma. The posterior is simply a Dirichlet gamma plus x. So I sample a parameter from this posterior distribution, and then I sample a synthetic data set that comes from the multinomial distribution I had with this new sampled parameter, pi tilde here. And here note that n, so this is a little more general. I don't need n to be the same as the one I had before. I could create a synthetic data set with a different sample size, but in general, we use n tilde equal to n. Okay, so this is the algorithm. And how do I get differential privacy? Well, the theorem that was in the paper is that you get differential privacy if and only if the prior you put on pi, this gamma here, is bigger or equal to this value here. So epsilon, that's the value of privacy that you get. And so you need to pick your prior depending on the privacy you want. And so this is a Bayesian model. We get differential privacy. You might argue that it's a little weird to be Bayesian and not put a prior distribution that actually just reflects your prior information about the parameter, but that's the price you have to pay to get differential privacy. So that was and so I presented here the Dirichlet multinomial, and it works for the sort of subcase of the beta binomial distribution. And so what I attempted to do is I wanted to extend this to more complicated models, and the goal was to produce synthetic data sets with differential privacy, because, so as I was saying before, just sampling from the posterior predictive might not be sufficient. And so at some point I had this short paper for the UNEC working session in Ottawa in 2013, and I proposed at that point to try and use the exponential mechanism. So I'll just show you a little bit what the ideas are. As I said, this is not quite workable, but just so we can all think a little bit about what it would mean to do that. So the exponential mechanism, for those of you who don't know it, it's a pretty standard way now of getting differentially private outputs. So suppose I have a data set with n inputs from some domain, and I want to release an output in some range that I call R. And so the idea is that you define some function that takes that takes a data set, and so you take what data set and a possible output, and you compute some value in R. So we call it a score function. You can pick any score function you want, but in general, what you need is that a higher score should mean that the output R you're thinking about is appealing output. It seems like a good output. So so in general, right, if you didn't have any privacy, suppose that I have some database and I'm looking to output the mean, and I'm gonna say, well, then I'll think about all the possible means and I'll give them each a score. Well, if I didn't have privacy, I would just always output the real mean, and that one would have score 1, and everything else would have a score of 0. But for privacy, what you do is that you say, well, maybe I won't output actually the mean, but something close. And then you give high score to things that are close to the true mean and low score to things that are further away. And then what you do is you sample one of these outputs with probability proportional to this here. So the exponential of epsilon over 2 delta q times this score function. And so the higher the score, the higher the probability that the observation is, that the output is sampled. Okay, and so what you need is you need to have a list of possible outputs and a score function for that output. And this has been applied in a lot of different contexts, and the idea was to think about trying to use that to sample from the posterior predictive distribution. It's pretty easy to pick. Well, you can imagine different score functions. The hard part with this is that you need to compute delta Q. So this is like the sensitivity when you do Laplace noise addition. So you need to pick, you need to compute the difference, possible difference in this score function with 2 neighboring databases. Okay, so that's the exponential mechanism. And so the idea was to apply this to Bayesian posterior predictive distribution. And I started with just a simple example here. So it's a beta binomial model. And so suppose that I just have a database which is just one number, like 5. And so you can think of this number as being an answer to a dichotomous question from a lot of people. So I ask a yes/no question to a bunch of people, and 5 of them say yes, and I want to output the value 5. And I'll put a prior that's a beta, so it's the conjugate prior. And so I can easily compute the posterior predictive distribution. It's not very interesting to look at the actual value. But the point then is what I wanted to say is then if you look at how to use the exponential mechanism, then you'll output. So you have some input x, like 5. And then you'll think about the posterior predictive distribution for all possible values. So if I have 20 people, it would be 0 to 20. So the possible values, the 5 was the real one. And then I'll come and look. So in this posterior distribution, it's the probability of having some specific output given the real data I have. And those are incorporated here and here in a few places. And then, so if I want to actually sample a private synthetic data set, then for this data set R, I'll replace R here. So my A with R, and then the same thing with B, and that's just the formula from the exponential mechanism. So it gives us a way to sample synthetic data set instead of just publishing the real data file. Okay, so this is sort of this is applied in a very simple setting, but that's what I was working on. And so what I did is I considered a few different score functions. So in this simple setting, I'm just thinking about publishing one raw number. And so I could think that, perhaps I can just look at the Euclidean distance between the actual numbers. So if I want to publish, if the true value is 5, well, I should give higher probability to publishing 4 and 6 than 18, right? And so I could just look at the Euclidean distance, and I want the score function to be high for values are close, so I'll take the negative. I could also just look at that posterior predictive probability, which is what I was just showing on the previous slide. And I also tried looking at the log of that probability. And so, whoops, oh, sorry, I did something wrong. 1 second. All right. Okay, so I considered 3 different score functions.
May I ask a simple question, please?
Yes.
If you output several synthetic data sets and average over them, will you not get back to the true value?
Yeah, so with differential privacy, if you were to output several synthetic data sets, you'd have to do it with a smaller value of epsilon. So if I want to output 10 data sets and I want overall epsilon, I'll have to output each with epsilon over 10. But so here I'm just considering one synthetic data set, but you're right that if I want to output more, then I'll have to do that. And so, because otherwise, you know, you could sort of use all the data sets to infer back the real data set. Does that answer your question?
Yep.
Yeah.
I thought.
I don't know if everybody hears the questions, so maybe I'll make sure that I don't know if I'm the only one that can hear you. We'll see. I'll try to make sure for that the next time. Okay, and so for each of these score functions, I need to compute this delta Q for all of these cases. And so in this little scenario, and it was very easy to do it by enumeration for the simulations I was doing, so that's what I did, right? So you have to take every possible neighboring databases and then compute the posterior predictive distribution and look at how that will vary depending on the 2 neighboring databases, and you can compute that delta Q. But that does not scale well with the size of the data sets or the complexity of the model. Okay, so as I was saying, this is really not applicable work right now. But just to give you an idea of what I get, so I applied this for a small example where I have 50 observations. So that means that my real data is something between 0 and 50. I either had 0 yeses or 50 yeses or anything in between. I want to output something that's between 0 and 50. So my output space is between 0 and 50. The true data set here was 30. I used epsilon of 0.5, so sort of a pretty small epsilon. And then those are the values of gamma. And so what I want to do is I look for every one of the score functions. Well, what's the most probable outcome? It's going to be 30 in all cases because that's how I design my score functions. I want them to output with higher probability the true database, the 30, but I have to allow for other things to be outputted. And this is just some sort of like descriptive statistics of what happens when I do this. The expected outcome. So if I use a score function that's the Euclidean density, I have the closest expected outcome. So on average, you know, in expectation, what the database I would output. Of course, I'm not going to output something that has that's not an integer, because my output space is 0 to 50. But this is just to give us an idea of seeing, you know, is it sort of an unbiased output in a sense. And then here's the expected distance to the true data set. And so the expected distance to the true data set, well, we find that if I just use the posterior predictive probabilities, I have a pretty high expected distribution to the true data set, which is why I started looking at this log here, because in my exponential mechanism, I take the exponent of that score function, and I thought, you know, maybe I should take the log, so I go back to actually sampling with proportionally to the posterior predictive probabilities. So this seems to work better here. But the log is a little harder to bound, because if I just look at probabilities, it's between 0 and 1, and so I could extend that to any case. I know it's going to be bounded by 1. It might be very big of an upper bound, then maybe I'll have sort of too private a data set, but at least I could do something and have a privacy guarantee. And then this is the expected posterior probability. So basically every one of my output in my output space has associated posterior probability, and I just take the expectation of what I would output with the exponential mechanism. And here it's small, the probability is higher again with the Euclidean distance. But so here it works with the Euclidean distance, but the thing is that this is a very, very simple example where I can actually compute a Euclidean distance between my outputs. But I looked at other things because in general, I would like to apply this to any complicated Bayesian model. So maybe I do, I can do any Bayesian model, and then for all of these models, I can definitely get a posterior predictive distribution, but I might not be able to get a distance between the data sets if my outputs are bigger data sets than just one integer. Okay, so this is just an idea of the things that I got. And so there's a lot of unanswered questions. I don't know what's the most appropriate score choice of score function. I don't know how I can calculate the sensitivity better if I have more complicated models. And it's not clear if the exponential mechanism is the way to go or if something else would work better. But it just seems nice because with the Bayesian models, I already get some score function, which is that posterior predictive probability. And so this is sort of where I was at when I thought about writing this, giving this seminar, just to get some other people thinking about the questions. And then somebody emailed me this week, and so I thought I should let you know. So he emailed me, telling me, oh, I can't listen to this talk, but here's a bunch of things that I saw that are related. And so you'll have the complete references at the end of the slides. But since then, people have been thinking a little bit more about getting Bayesian inference with privacy. And so there's 3 papers here that I've just skimmed because I got them like a day or 2 ago. So I don't know exactly what all the results are, but there's some more results here. And maybe we can take a look at that and try to actually implement it in sort of practical applications. Okay, so this is like the first part. And now I'm gonna flip. And so we haven't really solved the first problem. That was not the goal. And now I'm gonna talk about EDP. And I guess not that many people maybe know of EDP, so it's gonna be interesting here because I first tell you about EDP, and then I'll tell you a little bit of some results that we have about this measure. Unless there's any questions about the first part now, we can come back to it later. Yes?
To what extent do you rely on the people, if you put the data set out into the public domain, to what extent do you actually rely on people understanding differential privacy? Because you're saying, oh, you can't identify anybody, but they might make, people might try to make a rough match and then say this is a match.
Right, so I guess that's some more general comment about differential privacy, in that the privacy protection of differential privacy seems to depend on people understanding differential privacy, because otherwise they might try to make matches and think that it works, whereas it shouldn't really work. So I mean, I guess here I'm sort of taking as a given that differential privacy is an interesting notion of privacy to be looking at. And the idea is that you can sort of, everything sort of depends on people understanding the measure. If you do swapping, people can still try to identify records, but then you have to tell them, oh no, but we swapped, so you shouldn't be able to. So I guess I'm not really concerned with that here, but that's a whole other discussion about which methods should we use to measure a rigorous measure of privacy. But I think differential privacy is nice because it's actually sort of rigorous, and you can think about it independently of the actual data set you have, and so it's something that we can compare easily.
Thanks.
So I'm just sort of thinking that differential privacy might work and should be a good way of doing it. Yes.
So I've got a question for you too, Anne-Sophie. Going back to what you said you were going to talk about was one approach of publishing private draws from the posterior predictive distribution as a synthetic data set.
Right.
That's a little bit like in SDC what they call input perturbation, where you perturb the microdata set and then make it available for analysis, right?
Yes.
But you also said you were interested in publishing draws on information about the posterior distribution of parameters of interest.
Yes. So I guess I didn't look at that. Yeah, because that's a good point. I should have made that clear. So at the beginning, I said there were two things we might be looking at. One, publishing outputs from a synthetic, like output from posterior predictive distribution as synthetic data set, and the other was to look at publishing parameters. In this first part, I really myself only look at publishing synthetic data sets. But these three papers here on the slide, they are looking more at publishing outputs related to the posterior distribution.
So is that like, you know, the output perturbation, or is it the parameters of the synthetic data set, or is it the parameters of the analysis of interest on the synthetic, on the data?
So
That's what I'm interested in.
yes, I mean, so there's lots of ways you can think about publishing information about a posterior distribution with differential privacy. You could think about getting the real values and then adding noise, or you can think about adding the randomization process in the way in which you learn about the posterior distribution. So I'm not sure how to classify it in various, yeah. But so the idea here would be the same if you wanted to do, you could think about, and I think that's done in one of those papers, is think about the exponential mechanism but applied to the posterior distribution. And then you still have this sort of score, right? Because you have a posterior probability for each of your parameters of interest. And so you can think about sampling in that way, sampling one output from the posterior distribution. And so it's kind of similar, and you run into the same problems of having to compute sensitivities and, you know, like sort of get this bound to know how much noise you need to add. But in the second part, I guess, yeah, so maybe I should have made that clearer, but now in this EDP, here I'm really more looking at privacy for outputs of the model, so for the posterior distribution, because that's how it's been proposed.
Okay, thank you.
Before
Yes.
we leave the first part, the Bayesian paradigm doesn't really get around the problem that for some data sets you may have chosen a particular statistical framework and give me a synthetic data set from that perspective. But the reason I want to analyze the data is because I have a completely different statistical framework which I wish to apply that has nothing to do with your model. And now I've got your model contaminating my synthetic data.
Right. Yeah, I mean, so that's always the problem. If you are going to generate some synthetic data sets, there's always the issues of, does my model fit with the model you're then using to analyze? But the idea is that by trying to make the model sort of more general and capture all the interesting things in the data set, the hope is that it's gonna sort of fit with more models from the analyst. And what got me interested in these Bayesian models was that there was sort of a lot of development in getting more and more complicated Bayesian models to be able to capture sort of non-parametrically, in a sense, more complicated data sets. So there's a few papers by Jerry Ryder and some of his students, and I don't have the citations right now, but where they look at like Dirichlet processes and mixtures of Dirichlet processes for modeling contingency tables, and that can take into account the sampling zeros or the fixed zeros and all that sort of stuff. And so there's this sort of good machinery for trying to model the data set in a way that you're really trying to capture everything about it. And so these models could be useful for generating a synthetic data set that might fit with more analyst models. I'm not saying that it's gonna always fit the model of the analyst, but that was sort of the reason why I was thinking about it, is that I saw Bayesian models as being able to model pretty well some relationships. And so I wanted to see if we can make those, but with privacy.
Yeah. But there is indeed kind of a parallel effort in understanding. So if you understand how the synthetic data were made, then how do you adjust your analysis as well? So that's a really active research area too. Yeah.
But I mean, in practice, the people who hold the identifiable data
Yep.
seldom have the skill set to generate synthetic data. Tough enough to
Okay.
get them to de-identify the data in a credible manner, to get them out there to you in the first place.
True.
Even the concept of de-identifying can be badly interpreted both ways. Anyway, enough said.
I mean, in the
We're definitely raising, so I guess this is this first seminar in the program, after the opening workshop, so it's good. I think we're thinking about all the issues that we should think about during this program now.
well,
Well, at least a lot of them.
at the moment in England and Wales, there's a very authoritative central setup that is actually refusing to give the full date of death. So you get month and year, but not the day, as a sort of inane global rule, inane in my view, global rule. And the chances of them doing anything like this,
Yeah.
it's really quite serious what's happening to epidemiology.
Yeah, I mean, in fact, some years ago I took what Sheila is saying slightly more seriously, having looked at a lot of work that was worried about informed consent, which is the other side of privacy, and concluded we should just not be funding epidemiology if we want informed consent, because you can guarantee that your results will be wrong, seriously wrong, not just slightly. But that's, yes, I suppose there's interaction between how one can advance theory and then how one actually relates that to the people on the ground.
Right, yeah, I guess there's a lot of work from taking the ideas, from theoretical, I feel like I'm very applied theoretical person, but actually like implementing them in real life, then there's always a gap. But I think we need to be able to think about what privacy we can guarantee, like what as statisticians can we say about the data set that we publish, and then there's a whole lot of public discussions about, what we can allow, what we can't allow, and, what we should find, all of that. But yeah, this is a much more basic considerations here than I guess what you're talking about. All right, so maybe a few words about EDP now, and then we can continue discussing a little bit. So EDP as an alternative. So basically, I was doing this work with differential privacy and trying to have more complicated models. And I see some people have gotten some good success with it, but for me, it wasn't working very well. It was kind of hard to get a handle on these sensitivities and to get good answers. And so EDP, that was the idea, is that EDP was proposed as an alternative, and it's presented as a convenient way to obtain an empirical analog of epsilon. So the idea is that, okay, you are not able beforehand to design a method that will give you differential privacy. Well, just do whatever model you want to do, and then from looking at this model, you can try to estimate what differential privacy you kind of have in there. So that was the idea. It was proposed in 2013 in that paper by John Howard and some colleagues. And so they applied it to some Bayesian linear mixed models, and then later to Bayesian generalized linear mixed models and zero-inflated Poisson models. So they've been applying to a few sort of complicated models for which, at least when they started, and I don't know if the papers I just cited about Bayesian modeling answer the question now, but from a more practical person, there was no way of doing this with differential privacy. And so the idea was to use empirical differential privacy. And so here's what empirical differential privacy does. So you think about your original data set, and then you consider all data sets where you would remove one observation. Okay? So those are D minus I. And then consider one parameter theta that you're interested in. And then you have to discretize its posterior distributions into bins. Okay, so and you want the bins to have equal probability. And so you make these bins B1 to BB such that the probability that theta is in any bin for the posterior probability given your original data set is 1 over B. Okay, and then what you look at is you want to compute these two quantities. So you look at the probability of theta being in that bin if you had a neighboring data set to your true data set compared to what you had in the true data set. And then you look at the max and the min of that. And you can sort of see that this is, the flavor of differential privacy. You're trying to look at how your posterior distribution changes as you change the input. And here the input is changed between D and D minus I. And how the posterior changes is in terms of difference in probabilities in some discretization of the posterior distribution. And then you compute this thing, which is the max of the log of M1, M2, and this you call epsilon, and this value is the level of empirical differential privacy, which is considered to be an estimate of differential privacy. And you can do this, you don't have to think about this ahead of time. You can do it with any data set and any model you're interested in. A small little note here, it's not that important, but in the actual original paper, they consider more than one parameter. But then there's an assumption that the domains of the posterior distributions are the same, and in the example here, I'm just using one parameter, so that's why I stated the definition only with one parameter. Okay, and in practice, you have to get those probabilities, and what you do, well, you're Bayesian, and you usually just sample from the posterior distribution, and so it's pretty easy to estimate those from the sample draws of the posterior distribution. And so in practice, what you do is you'll estimate M1 and M2 from sample draws. And so you start by getting draws from the actual posterior distribution for theta given the real data you have. And then you compute quantiles from these in such a way that you get intervals with the same probabilities. And then the probability of theta in these intervals is 1 over B. The number of bins, and then you remove each observation I from your true data set, and then you resample from the posterior given that D minus I, and so you do that for each observation in your data. You remove it and you get some new draws from the posterior distribution, and then you can estimate the probabilities of the probability for each of these bins by just taking the count, the proportion of observation in that bin in the posterior distribution with one observation removed. Okay, so I hope that makes sense. That's the ETP procedure. And you have to pick, so to do this, you have to pick M and B. So M is the number of draws you'll take from your posterior distributions, and B is the number of bins you'll look at. And so the values in the paper, the original paper, were 10,000 and B equals 20. And how you're supposed to use this, the idea is it's kind of like in the Dirichlet multinomial example I showed before. In the Dirichlet multinomial example, we saw that to ensure differential privacy, you had to tweak your prior a little bit. There was this bound on the parameters in your Dirichlet prior. And if you make the prior sort of more flat, then you'll get differential privacy. So it's the same thing. You start with some prior for data, and then you do the whole process that I just described, and you'll get an epsilon. And say you get epsilon of 5, and you think, oh, e to the 5 is pretty big, that's not good enough. Then you go back and you change your prior until you get sort of an epsilon that you like. And so if you have a more informative prior, then you'll have, so in general, more informative, you'll have higher privacy because the prior, you think of it as sort of a uniform prior. And so you just play with the prior until you get an epsilon you like, and then you can output information about that posterior distribution, and you can quote the EDP associated with it. Okay, so that's the intended use, and the whole point that you pick. So the point that you pick the prior, depending on the epsilon, that's not very discussed in the paper, but if you're sort of a strict differential privacy person, you'll see clearly that this might leak some information about the actual data because you took data chosen prior but did not take that into account when you compute the epsilon. But let's say we'll gloss over that for now. But that was sort of the proposal. And so About and some of his colleagues, they applied that to 3 different models with real data sets and large scale data, and they would output information about the posterior distribution, and they would also compute this EDP epsilon and give some sort of guarantee about the privacy of the output. And so where I come here is that I thought it was a very neat idea because you could sort of do it for any model without having to recompute a bunch of sensitivities and get a complicated methodology. So I started looking at this with a student, and we have a paper that's going to be published in JPC soon. And so we looked at what this EDP really meant and what is the limits of it. Because so in the papers it's presented, it's used as a tool to do analysis, but there's not that much thinking about what it really means and how it's different from differential privacy. And so we have 2 main conclusions. I just give you an idea of them now, but you can look at the paper if you want more details. But the first sad news is that this EDP is not at all an empirical estimate of differential privacy. Okay, so we were a little excited, we started playing with it, but we found out it really doesn't work that well. There's 3 big reasons. One is that we're implicitly conditioning on the real data that we have at hand, right? So I say we look at D and D minus I. That's not what DP does. Really, it should be you should think of it more as a sensitivity measure, actually. And there's a big impact on the choice of discretization. So I'll show one slide for each of these 3 problems. And then the other thing we found is that they suggested 10,000 iterations, but we found that you need way more than 10,000 draws from the posterior to have good estimates of this value. And we could find that because we actually apply it to simpler models than their complicated models, where we could also compute the real M1 and M2, the real probabilities, just by knowing the form of the posterior distribution and not from sample draws. Okay, so maybe I'll take like 5-6 minutes to just give you a few details about some of those, but it's all written in the paper. But so the first, the implicit conditioning, well, it's pretty clear that that's an issue because you don't look at all neighbor pairs, right? You only look at D and D minus I. And so sort of thinking about it, it's kind of like if you were trying to think about a conditional differential privacy. So we made up this definition here just to see what the difference is in differential privacy, you have all possible neighboring database. But here you're sort of thinking about a conditional differential privacy where you have just D and then D minus I for all the observations in your data set, and you're just looking at these ratios. Okay, so that's sort of more what you're trying to estimate. And EDP, I said EDP, but CDP and DP, the epsilons will not be comparable. You don't get the same thing with conditional differential privacy than with differential privacy. And well, here's a small just illustration of what happens. But say I set DP to 2.4, and here I do my beta binomial model again, so I know how to get differential privacy. And so if DP is set to 2.4, well, 2.4 will be, so on the x-axis, I have different values of n, different sample sizes. And on the y, I have the CDP. And for each sample size, there's a lot of different CDP values because what happens is the CDP depends on the true data set. So for each true data set, I can think about looking at all the neighboring data sets for that, removing an observation for that true data set, and I get a bunch of different CDP values. And the differential privacy 2.4, that's the maximum of all these. Because differential privacy, that's, it's a worst case guarantee. You put a bound on the worst possible ratios of these probabilities. But if you have some data sets that are not as extreme, then you'll get much smaller values of CDP. And so if you're just trying to take CDP as an estimate of DP, then you're going to get, most of the time, much lower values than the real one. And then here, I increase epsilon, and you see sort of there's a lot of true data set for which this conditional measure is much smaller than the true 5. And I think, most people knew that, but we're just sort of explicit here about the fact that because of that, as a start, DP and EDP really can't be sort of similar measures. All right. I won't go into too many details now because of time, but you can take a look if you're interested. The other thing that we realize is that really EDP is more like a sensitivity measure because, and I'll just write that here, but maybe I won't go through all of this discussion, but the whole point is that differential privacy is a property of a randomized function. And so you don't say a data set is differentially private, you say the data set was generated with a function that's differentially private. And there has to be some randomness in that function. With EDP, you have a fixed data set and you have a fixed model. And you're looking at like the posterior distribution. And that posterior distribution, that's just fixed, that just exists, right? So it's a posterior distribution. And so you're not thinking about the property of a randomization function now, but of an output of a randomization function. And you look at the difference between different outputs of that randomization function. And so what you're really looking at is you're really computing a local sensitivity measure for that posterior distribution. And that specific measure is this the way you decided to define distances between posterior distribution with this M1 and M2. And so it's really more a sensitivity measure than it is a privacy measure, when you compare it to differential privacy. And so usually when we have these sensitivity measure, we use them to compute how much noise to add in the randomization function, but it's not a measure of how private that function is. So there's this sort of weird association between something that's measuring sensitivity and something that's differential privacy, and it's not the same thing. And then the last big reason why there's an issue with estimating EDP from DP is that we choose that number of bin, and it turns out that so in the paper I said they use 20 bins. And that's what they use in all the papers, I think. But it turns out that it changes a lot depending on what you choose as the number of bins. So maybe I'll just show you already the graph. So basically what happens is as you increase the number of bins, you automatically get a higher epsilon with empirical differential privacy. And basically, like when you look at them with finer and finer bins, well, you see bigger differences between the posterior distributions. And this is just a quick graph here. To show you sort of, what I've been saying is that I have the value of B here, and here I have the true theoretical empirical differential privacy. And why I call it true is because here I use a simpler model. It's a normal conjugate model, so I have a normal prior, and I have a normal likelihood. And so in this case, I don't actually have to estimate M1 and M2 from draws. I can just, I know what the posterior distribution is, and I can just look at the probabilities for different quantiles of my normal distribution. So I get the true, I call it the true EDP. And so this varies with B. And here there's draws from 100 different data sets. Because for each data set, I'll have a slightly different value of EDP because for each data set I have, then I need to remove all the observations in my data set. And so if I have a different data set, I remove different observations. And so I have a slightly different value of EDP. And I have different sample sizes at top here, 100 observations, 1,000, 10,000. And we see that as B increases, then my value, that EDP epsilon increases. And we did the same with beta binomial model. And so the point is that, this measure, it's not even fixed, right? Like the measure, this EDP epsilon, it depends on B. So really we should be thinking about a B EDP epsilon. And then we need to decide, what B should be. And then the last thing we have in that paper is thinking about the computational burden. And so I'll be really brief here. The details are there, but you think about, usually the M was 10,000 draws. So you'll take 10,000 draws from the posterior distribution, and you have to take 10,000 draws for each of the posterior distributions. And since we applied EDP here to simpler models, so the normal model and the beta binomial model, we were in both cases able to compute the true EDP. And then we also estimated from draws of the posterior distribution. And so they couldn't do that in their example because they had way more complicated models, and so you couldn't get the true, you had to sample. And we find that way more draws are required than 10,000 in general, and I'll show you a graph in a minute. And we also find, so they suggested a criterion, which I won't go into here, but they suggested a criterion to decide if M is large enough, and this criterion does not very work well in all of our simulations. And so here's just an example. So I still have the normal model. So here on the x-axis, you have different values for the number of bins. And here is my estimated epsilon. And the red lines are the true values I can compute theoretically. And if I take 10,000, well, we see that I'm doing a poor job no matter what number of bins I have. And 5 is a pretty small number of bins, right? It's harder when I have more bins because then I have less observation in each bin, so I'm trying to estimate smaller probabilities. And the whole difficulty here is that I'm trying to estimate the max and minimum difference in these probabilities. So it's very small probabilities that are usually problematic, so that makes it really hard to estimate. And if I increase to 10,000, well, now I get much better estimation for B equals 5, but it's not that good yet. And everything sort of gets a little better. And then I need 1 million here to get a pretty good estimation with 5 and 10. So we have in the paper the actual sort of numerical description of this graph, but I just put the graph here for today. But so, and like 1 million, so now we need 1 million draws from the true posterior distribution, 1 million draws for each of the distributions without one of the observations. So imagine a large data set, it just gets a little complicated. And so EDP, well, it's not really an empirical estimate of DP. It could help in some way measuring local sensitivity for Bayesian model, but then we need to decide what to do with B. And I don't know what to do with B. And then this way of estimating M1 and M2, there's probably better ways. If we decide that we want to work on this EDP and do something with it, there's probably better ways to estimate M1 and M2 with some sort of like different sampling, because we're really interested in some specific values. All right, now I have 5 minutes left and I have one conclusion slide, so let's just see. So overall, what was the point of this discussion? Well, I want to talk about privacy for output of Bayesian models. The first part was talking about how the exponential mechanism could be used to generate private synthetic data sets by sampling from the posterior predictive distribution, but there's this complication of I have to compute sensitivity. EDP was proposed as a way to make this easier. You don't have to have theoretical results, you can just do the analysis and then sort of compute by brute force basically one measure of privacy. But our analysis really shows that you can't really use it in that way. You can think of it differently, but you can't just use it as an empirical estimate for the DP. And then I pointed out that there's a lot of recent work, well, a few pieces of recent work about privacy for Bayesian modeling. Can we use these in applications? Could we think about doing, synthetic data sets with Bayesian models with this privacy guarantee? Should we think of privacy differently? I don't know. This is all for future work. And now we already started discussing, but there's a little bit more time for questions and comments. And just to show you, there's references here that I quoted in the talk. So, yes.
You have to say whom you're giving the right to speak to.
Sorry, I can't hear very well. I don't know if the mic is not as close to you.
Okay, so I have, I think, 2 questions. So
Okay.
Can you hear me?
Yeah, I can hear. Okay. So I tell, but it should
Okay.
work.
So differential privacy, so there's a randomization algorithm, and there's a space of potential data sets over which it's supposed to be able to perform.
Yes.
Why? So I'm asking you because it seems like you've thought about it a lot. Why can't I say this is my data set, and my data set is my space? I'm not interested in anything else. I want differential privacy with respect to the data that I have, and that's it. I will compute sensitivity with respect to this data set, but everything is under the definition of differential privacy for the given data set.
Right. So I think one of the problem, one of the problem with that is that once you output, because with differential privacy, you're also supposed to be allowed to say what the mechanism was that you applied. And if I say what epsilon is and what mechanism I applied, then somebody could use that to infer information about my specific data set because they'll know, say, oh, he must have had an extreme data set because then he needed to add that much noise, or he could have had this data set because then, that much noise would not have been sufficient to guarantee this epsilon. So I think that's the main problem with trying to have sort of differential privacy for a specific data set is that by saying that you were able to get this epsilon for this specific data set, you're revealing something about the data set you have. But there's a few other people, so I've heard this idea, but I haven't seen it in print anywhere. But people have been thinking a little bit about having privacy just for the data set that you're interested in. And one example is like this random differential privacy where you're thinking, but it's not even that though. I think it's really hard to think about having privacy for just the data you have without revealing too much about the data you have when you say what you did as a mechanism for protection. And we want to have these mechanisms published because then the analyst can take it into account in his analysis. And so that's one really nice thing about differential privacy is if you tell me what you did, I can sort of use that in my analysis. And I did that in the paper a while ago where I was thinking about this Dirichlet multinomial model, but you protect the data set with differential privacy, you tell me how, and I include that in my model, and I can recover accurate inference. And so that's why you kind of want to say what you did. But once you say what you did and give a privacy value, you can sort of learn something about the true data set that you have.
I understand your answer. However, suppose I'm a person who has 10 data sets altogether, and this is all I'm going to publish. I'm a researcher. I'm about to retire and I want to publish my data sets. I have 20. Then I should artificially increase my space so as not to reveal. I understand your answer. I should artificially increase the space to places where I'm never going to be just in order to defend my epsilon. It's like your answer is fine, but puts me in a strange position also. Do you see my point?
Yeah, no, I completely see the point, and I would love to see a privacy definition that doesn't do that, because it is very annoying to have to think about all these data sets that I will never get, and I'm probably never going to get. And so I guess like some relaxations are this, there's the delta epsilon, so there's two different, I know of at least two different delta epsilon differential privacy, and one of which, the probabilistic delta epsilon, is something like I want to make sure I have epsilon, but except for databases that are very unlikely. So I'm not going to remove all the other databases from my space of possible databases, but I'll put like a probability value to all of them, and if they're very unlikely, I won't require the epsilon to hold. And so that's one way you can think about doing it. And there's this, so in this random differential privacy too, that's where they think about, you don't necessarily add or remove any possible case in your database. You think about adding or removing a sample that is similar to the other observations you have in your data set. And so that's another attempt, people trying to sort of bridge the gap between what the researcher would like to do and what our privacy measures can say for now. But it's not always perfect, right? Because if you're an outsider, like if you're an outlier, you want to be protected. And if I say I'll protect against people that look like other people I have, then it's not ideal for you. So I think it's pretty hard to actually figure out how to do it. But yeah, and that's why when we had the program, I thought that thinking about other measures of privacy, like differential privacy, is working really well. They're proving a lot of stuff, and now there's very interesting results about how it can help to reduce overfitting and things like that. But I'm not sure that it's the only solution, and there might be something that would work better in practice, but we need to try to make it rigorous, and that's hard.
And another question, the way I understood the first part of your talk is simply a Bayesian way to generate artificial data. I don't see it as a way of protecting anything in Bayesian analysis. I don't know what you have in mind. I'm not sure now.
Yeah, so maybe I wasn't that clear when I thought about that first. So what I did was indeed a Bayesian way of producing synthetic data. Because the score function I was looking at was difference between output data sets. But the exponential mechanism could be applied for output from a Bayesian model if you look at the score function being just simply the posterior probability in your posterior function, in your posterior distribution, sorry. Right, so I think the idea could be applied, but I guess at first I started to do both, and then it wasn't working super well, so I didn't try to apply it to output of Bayesian models. But the whole point was trying to do something that uses Bayesian statistics and have it be private, because I didn't know how to do that except for the on the map example. So I guess it was sort of a more general idea of trying to do something Bayesian and have it being private, and I started with synthetic data. But it could also be output from a Bayesian modeling. Yeah.
Thank you.
I tried to link two things in this talk to have something to talk about, so maybe the link wasn't super clear.
I think you touch on an important distinction between privacy of the data and privacy of the individuals about whom the data are. And certainly in health, when we talk about data privacy, we mean protection against de-identification or re-identification of the individual whose data these were. So that, for instance, they tell a story in Scotland about electronic tagging of an offender who had an artificial leg. And he took off his leg and went off on holiday and breached his parole, but the leg was beside the console, so he appeared always to be there. Now, if his criminal justice record were linked to his health record, and for example, he was HIV infected, then the prison service who'd released him on a tag with an artificial leg, and they're never going to do that ever again, certainly know that man's HIV status if he still remains in any data set, because he's only one.
Right, well, but I guess the goal here would be to not publish the true data set, but to publish a synthetic version of the data set where perhaps that person is, the person wouldn't exactly be there, and there might be in the data set, depending how you make it there. I guess if he's the only person with those characteristics, maybe there's not going to be someone like him in the data set. But the whole point is that
Not in Scotland's data set, but there might well be in other countries who make the same mistake.
Now, if the prior is that there ain't no such person, then also the posterior, and this person is washed out and disappears.
right, yeah, exactly. So if you start by assuming, well, but that, what that would do, that would be restricting your space of databases we're talking about. So if I'm saying there's no space of database where somebody has a fake leg and has a thing on this fake leg and has, then I restrict my space of databases.
Yes.
Yeah, and I think that's a promising, line of relaxation for epsilon differential privacy, is to look at what your population is, and therefore what
Needs to be protected.
what data sets are likely to arise from that population. So yeah, taking that extra step to the population, which we kind of ignore in this, in the formal differential privacy theorem proving exercise,
Yeah, and there's a few attempts, like removing from your space those that are not as probable, those that have small probability of being produced by your randomization function. But yeah, there's still lots of work there that could be done on thinking about, because then you would need to add less noise, right? Like if you don't want to protect all possible databases.
That's right.
I think one reason why I think this is not Bayesian analysis, but rather Bayesian way to generate synthetic data, is that you say, okay, so this doesn't work, let's change the prior. A true Bayesian,
I know, yeah,
it's not Bayesian analysis.
And I did acknowledge that. I think that, for a true Bayesian, this is all very weird, because the point is you have a prior that represents nothing of your prior information, but that mostly represents information about how much you need noise to get privacy, right? But those are the only, I guess, playing with the prior is the only thing I've seen to get differential privacy for a Bayesian analysis. But as I said, there's these more recent literature that I haven't looked at too much, and they might more, I think it just was easier to play with the prior, but maybe if you change the likelihood function a little bit, you could also get something that works. But you have to do something, right?
This is why I say that I don't, as far as I understood, I may be wrong, I don't consider it Bayesian analysis. I consider it to use Bayes' formulas, Bayes' formula in particular, to generate data. And then you're allowed, if you don't like this prior, change the prior, and you generate another data set. And you can choose a prior that rules out some characters that you want out of the posterior, don't want to produce them, and that's fine. But it's not Bayesian analysis.
It's opportunistic.
You're washing out the
Right, well, okay, so maybe in the first part, but like if you talk to John about, and his colleagues in the second part, they really wanted to do a Bayesian analysis. But, they needed to have some privacy guarantee. And if you're not allowed to change anything about your Bayesian analysis because you really want to be truly Bayesian, it's going to be hard to give some privacy guarantee, I think.
No, you can, in principle, you can do Bayesian analysis, get the output, and then decide what noise to add to it. So I think this is a different story.
Okay, so you think there's a fundamental difference between adding noise to the output versus changing a way to get the output?
No,
Yes.
Anyhow,
Yes,
I think
that was what I was asking about. Yeah.
Bottom line is I see, and unless you explain more, but maybe you can, I see it as a way to generate synthetic data using Bayesian techniques.
Yeah, that's definitely the first part of the talk. What I presented was that.
Someone told me, the following story appears in the memoirs of Lehman, Eric Lehman, the statistician. So someone, maybe Lindley, gave a very Bayesian talk, computed some priors, and it didn't work out very well, so he said, let's change the prior. So someone in the audience says, I think it's better to change the data. So a true Bayesian cannot defend his position once he changes the prior.
Yeah, no, I mean, I know all that, but, and I never claimed that I did acknowledge that, true Bayesians would not be happy with what we're doing here, because to get privacy, we change the prior. But yeah, it's a trick to get privacy guarantee.
Well, perhaps what you've done, Anne-Sophie, is invent a whole other sort of analysis in which it isn't a prior, it is actually, your privacy
Mechanism.
your privacy amount.
You're right, yeah.
You might
So
need
it's
to
a
call it.
privacy mechanism inspired by Bayesian analyses.
There you go.
You guess how I should have called the talk.
That's voila.
Can I ask one final?
All right, so that's the post name for the talk. That's how I'm calling it now.
Can I ask one further question about the last part, where you
Sure.
did this, the study on varying the M up to 1 million?
Yeah.
Was it not relevant how many were actually in the database, the N? You talk about B EDP, but
Yes, fixed N.
Oh yeah. There's a big relationship between how big.
Yeah.
So here we're not saying that 1 million is a good M, because if you change the N, it
exactly.
simply changes how big the M has to be.
So is it not a
right.
relationship with N over B? So rather than B EDP
yeah, perhaps
epsilon, it's N over B
Yeah.
EDP.
Oh,
Epsilon.
right, because that would be the number in each of, so we
Yeah,
didn't
the
think about
expected
looking at it that way.
Yeah.
But the whole point here was really that that it's way more than
Yeah.
they thought it would be, and they have a criterion they suggested, and we tried it, and it doesn't really work well to tell you if you have enough or not. But yeah, here this is just N of 100, but that's an interesting point. Maybe I can take a look at the N over B versus that value
And
of
it'll be
M.
in relation to
Yeah.
the count, just the sort of statistical power for any count.
Right.
That
Good
tells you how
idea.
to work out M.
Good idea. Well, but, though, I don't know, with what we think of EDP now, I'm not sure that we should spend too much time trying to prove it, because I still don't know what to do with B, Every B I pick has a different value of epsilon, and it's not clear which one more represents a measure I can make sense of, like try to use this in a real setting and explain this to your statistical agency. We should take B equals 10 because it represents, it's not very clear what we mean with it. So, but that's still a good idea to think about.
Very good. Well, let's, I think we will thank Anne-Sophie very much for definitely generated a lot of discussion. So thank you very much. And I acknowledge it's difficult over Skype, but you did a great job. So thank you.
Yeah.
All right, thank you for attending, and thanks for discussing. That was the whole point of this seminar, and I hope we have some other interesting seminars in the future where we can keep discussing these ideas.
Fantastic.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
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 Oh yes. I'll let you back in.